Alright everyone, we're going to do another couple examples of finding zeros of polynomial functions. Alright, so we're going to be using the rational zeros theorem. Alright, as shown in a previous video, the possible rational zeros are factors of the constant term divided by factors of the leading coefficient. So in this example we're looking at here, the constant term is 10, negative 10. The only factors would be, excluding the sign for the moment, 10, 5, 2, and 1. The constant leading coefficient is 1, so our only possible rational zeros would be 1 over 1, which is 1, 2 over 1, which is 2, 5 over 1, or 10 over 1, which is 5 and 10, plus or minus, including the sign could be positive or negative. Alright, now looking at the graph, it's not exactly totally clear whether 2 is a root or not. It seems like negative 2 should be a 0. Let's check this out. So we got to be a little careful, especially using a graphing calculator. Alright, unless we're going to use the trace features or the 0 feature on there to help us kind of really pin it down. We've got to be a little bit careful in believing it's not quite clear whether or not that is 2 or not. Alright, if that's a 0, it's kind of a question mark. Is that a 0 or not there? Well, let's see. Let's find out. Alright, so let's work with negative 2. So again, the idea is if x equals negative 2 is a 0, that's going to tell us that x minus 2 minus, negative 2, which in this case is going to give us x plus 2, will be a factor. So we want to use synthetic division, but we want to use it with the 0, the numerical 0, which is at negative 2, which we think is that from the graph. Alright, again, writing our coefficients down, we got 1, 2, negative 5, and 10. And again, hopefully we're getting faster at this process now. And this is a shortcut for polynomial long division when we're dividing by a linear factor of the form x minus a number. It always has to be x minus a number. So if we have x plus 2 we're trying to divide by, we have to remember that we're saying that negative 2 would be the 0, and that's the number in the box there. Then we multiply the number in the box times this number underneath the line, gives us negative 2. Add them together gives us 0. 0 times negative 2 is 0. Add them together, we get negative 5. Negative 5 times, okay, and I missed a sign here. That was supposed to be a negative 10 up top. I'm realizing that now. Negative 2 times negative 5 is positive 10. Positive 10 plus negative 10 gives us 0. Alright, so yes, us coming up with a remainder of 0 means that x minus negative 2 or x plus 2 is a factor. Once again, these three numbers here, again, this is going to give us the remainder, the 0. This is telling us our remainder is 0, and this is giving us the coefficients. So our coefficients are 1x squared plus 0x minus 5 of the quotient polynomial. Alright, now for our purposes here, we're trying to find the zeros. We're going to say then that, okay, f of x is going to be x minus negative 2, which I'm going to write as x plus 2, times what's left over is, we don't have to write down 0x. Alright, we can just put x squared minus 5 here. Alright, now that kind of shows us that, yes, that those other zeros aren't at 2. Alright, if we were at x squared minus 4, yeah, then we'd be at negative, then 2 would be a 0. To find the remaining zeros, we're going to want to set each factor equal 0. Again, that's our goal, is to find the 0. So if we want to set that equal 0 and solve that resulting equation, well, we already know negative 2 is a 0. We would really be setting x squared minus 5 equals 0. Now this you could use the quadratic formula on, or since we can isolate the squared variable, or the x variable here, we can square root both sides or apply the square root principle to get that x is plus or minus the square root of 5. Alright, now if you do that on a calculator, you're going to get 2 point something. Okay, so we can verify that we don't quite get 2, as again the screenshot I have in there indicates. I've got this plotted in Desmos. I'm going to go over to Desmos to look at that graph now. So I've got the polynomial we're working on. Alright, I'm just going to zoom in a little bit on the roots. We can see that's a little bit to the right of 2. That's square root of 2 is 2.236 rounded to 2 decimal places. The graph crosses twice actually over here. Once at negative 2 and once at negative 2.236, which is the negative square root of 5. The opposite of square root of 5. Alright. Excuse me. Okay, we're going to do a couple other examples hopefully in this video. I've got one more kind of queued up here that I've already done some of the work on. We can see in the picture here, and it's a cubic polynomial that's only got one zero, which is a possibility. All right, now looking at the rational zeros theorem, I've wrote out some of these steps already just to save time. The coefficients of the factors of the leading term are 1 and 2. The factors of the constant term 5 are just 1 and 5. So we're going to look at all combinations of taking factors of 5, which are 1 and 5, dividing by factors of 2, which are 1 and 2. So it gives us plus or minus 1, plus or minus 1 over 2, plus or minus 5 over 1, or 5, and plus or minus 5 over 2. All right, those are our really 8 possibilities. Now it looks like from the graph that it's somewhere between 2 and 3. 5 over 2 is 2.5. That turns out to be the only real zero in this case. All right, so if we were going to do synthetic division, we would want to use 2.5 or 5 over 2. I've done the work here already. Again, we bring the 2 down, multiply it by 5 over 2, which gives us 5. Adding gives us 2. Multiplying by 2 gives us 5 again. Multiplying by 2 again gives us 5, which shows that our remainder comes out to 0. If our remainder is 0, that means x minus 5 over 2 is a factor, and those are our coefficients. Now, what we're seeing here, I'm just going to underline this and then take it off. Each one of these terms has a factor of 2 in it. I might leave that in there. I'm just going to write it off to the side. And what we can do is factor out a 2 from each one of those terms in the second polynomial. I've done that and put that out front here. All right, now the one thing I'm going to add on here is I'm going to re-multiply the 2 through the parentheses there to get f of x into its factored form. All right, 2 times x is just 2x. 2 times 5 over 2 clears that fraction to give me 5. And then we get x squared plus x plus 1. And that's all I want to do for this example. We're going to do another one in a minute where we get some imaginary zeros. But it turns out this graph, we can see it only crosses, you can verify this with Desmos also, it only crosses the x-axis one time. It only has one real zero. If we set the other factor, the quadratic factor, equals 0, we would end up getting imaginary solutions, or complex number solutions. All right, so we're going to do another couple examples. The last one we do is going to have some imaginary roots in it. All right, this one here, it's a fourth order. We want to find the zeros and then write the fully factored form out. I have this one loaded into Desmos. I'm going to use that to help us come up with the possible rational zeros. All right, so I'm just going to look at the possible rational zeros, and we're going to just use the graph to help us eliminate the choices. There's a lot to choose from here. We have to look at factors of 375 divided by factors of 8. So let's avoid that by looking at the graph. All right, I added some of the factors. Again, using the rational zeros theorem would be doable, tractable, but not super feasible when we have Desmos at our exposure, at least for the purposes of this video. There's lots of factors of 375. There's 4 different factors of 8. We'd have lots of combinations for rational zeros, which we could test by hand. Again, it'd be very time consuming. I've got the graph loaded here. All right, I've kind of zoomed out. So you can see the scale. I've kind of zoomed out with the y-axis. You can do this with a mouse by kind of holding down with one of the buttons and scrolling out, or with your fingers by actually on the y-axis zooming out, and it'll only zoom out in the y-axis. You can also do a similar thing with x, but we can see 3 and 5 are some zeros. All right, notice this polynomial is degree 4, leading coefficient's positive, so it's got to go up as we go from, or as we go towards positive or negative infinity, and it's kind of got that shape to it. All right. And we can see from the graph that 3 is a 0 and 5 is a 0. So let's use synthetic division with 3 and 5. All right, so we're pretty sure that 3 is a 0 and 5 is a 0. Now finding the others, again, we can use Desmos, but we're going to want to try to do this a bit by hand. All right, in here. So using synthetic division with 3, we're going to have 3. This is going to be an example where we're going to have repeated synthetic division. Alright, just for time's sake in the video, I put some of the numbers in terms of our coefficients. Alright, so we've got those down. Now we bring the 8 down. 8 times 3 is 24, so we get 24. Add, we get negative 10. Multiply 3 times negative 10, we're going to get negative 30. Adding that together, we're going to get negative 125. If we multiply 3 times negative 125, we're going to get negative 375, if I'm doing my arithmetic correctly. Just check that quick. Yep, we're good there. And then if we add those together, we're going to get negative 125. Multiplying those together, we get negative 375, which is going to give us 0. And again, the 0 is important. That's our remainder. All right, now we could stop there, but we also thought that 5 was a 0. So what we're going to do is do a repeated synthetic division, and now we're going to put 5 up in the box here and repeat this with the cubic quotient that we ended up with. So now we're going to bring the 8 down again. All right, and then repeat the process. 5 times 8 is going to give us 40. Adding them together, we get positive 30. Multiplying 5 times 30, we get 150. Adding them together, we get 25. 25 times 5 is positive 125, which is going to give us, again, a remainder of 0. So we went from a 5-term polynomial, which is 4th order, to now 3 terms. That's our quotient polynomial. So now we're writing out the factored form. What we're going to see here, excuse me, is that the function f of x, well, we had 3 was a root or a 0, so we can have x minus 3 as a factor. 5 was a 0, so x minus 5 was a factor. What's the remaining quotient polynomial? It's 8x squared plus 30x plus 25. All right, now our job is to fully factor that for this problem, which we can now use either the AC method or the bottoms up method for. All right, and we also want to find the remaining zeros. And for the sake of just time for the video, I'm not going to go through the AC method for this, but I'm going to put down the fully factored form. Okay, you can again use the AC method or the bottoms up method. Either way, you'll come up with this factorization. You're going to get 4x and 2x, and you're going to get plus 5 and plus 5 for both. All right, we can just do a quick mental check on that. We get 8x squared, we get 25. 4x times 5 is 20. 5 times 2x is 10, so we'd get 30x. All right, now to find the remaining zero. So that's part of the question. We wanted to find the fully factored form, so we did that. To find the remaining zeros, we would set each one of these linear factors equal 0. We'd get 4x plus 5 equals 0. Separately, we would set 2x plus 5 equals 0. All right, subtract 5 from both sides, we would get 4 equals negative 5. Divide by 4, we would get negative 5 over 4. Over here, subtract 5, we would get 2x equals negative 5. Divide by 2, we would get negative 5 divided by 2. All right, now this comes out to negative 1.25 as a decimal. This is negative 2.5 as a decimal. Sure, we could verify this with Desmos or with a graphing calculator, but if you're asked to do it by hand, this is the process we would need to go through. All right, maybe use the calculator, a graphing calculator to help us pin it down, and then use synthetic division or polynomial long division along with factoring of the quadratic formula to find the rest. Again, we could have set the x squared plus 30x plus 25 equals 0 and use the quadratic formula to find these zeros. Also, if we want the fully factored form, though, better to look at the factored part. Just last thing for the video, if I go back to Desmos, again, Desmos is very slick in that we can click on these zeros and it tells us what those decimal equivalents are. We verified that by hand. All right, that's it for this video.